So as the name itself is indicating, this is the discussion we are studying about the behavior of a transformer when you try to switch it on from an infinite busbar. Assume we have an AC voltage source and a new transformer is there, and that new transformer is switching on. At that switching time, what are the transients experienced by transformer is the discussion. First tell me, transformer is a highly inductive circuit or highly resistive circuit? Yes, transformer is a highly inductive circuit with small resistance offered by winding of the transformer. Okay, we know the self inductance of the transformer is really high. Okay, because we are using very high permeability core, that's why self inductance offered by transformer is really high. Whereas winding of the transformer will offer a small amount of resistance, because our main aim is to minimize copper loss. That's why we will choose low resistance conductors. That's why I can conclude that transformer is a highly inductive circuit with small resistance offered by winding of the transformer. Okay, therefore before going to the switching transient discussion in a transformer, first let me discuss about a simple RL circuit, because our transformer is also like an RL circuit, and what is the transient current experienced by that RL circuit when you try to switch it on. Okay, so this is indirectly a concept related to electrical circuits. In network theory you will study more in detail, but here we will study briefly. Okay, let's see. So assume I have a voltage source with me, a sinusoidal voltage source, and this voltage source is connected to an RL circuit like this. Okay, this is an RL circuit, right? Now initially the switch is been open. From infinite period of time the switch is been open. Exactly at a time t is equal to 0, the switch is been closed. So the moment when the switch is closed, current started to circulate in this loop, and this current will have two responses. One is going to be transient current component response, another one is going to be steady state current component response. Okay, because we have a storage element here, definitely transient component will come into picture. Okay, now tell me, before the switch is closed, can I say the current through this particular network is equal to 0? And once the switch is closed, immediately the current will change or does not change? Does not change. We know the property of inductor is it does not allow sudden change in current. So therefore the total current that is in this loop at the time of switching on is divided into two components. One is going to be steady state component, another one is going to be transient component. So therefore I can write total current I will be equal to sum of steady state current plus transient current. Yes or not? So we know any RL circuit or RC circuit or RLC circuit, when you try to switch on, transient will be coming into picture. Now tell me what are the basic expressions for steady state component and transient component. I am writing directly. Okay, you will study in network theory more in detail regarding that. Okay, natural response, forced response. Okay, and using a differential equation, it's a first order circuit. Okay, you can find out transient component as well as steady state component. Suppose you assume this supply voltage source Vs is equal to sinusoidal voltage source, let us say Vm sin omega t. Alright, this is the supply voltage source value. Therefore, what will be the steady state current component? Steady state means, can I say it is the component which will be available permanently? Yes or not? Okay. Whereas a transient component means it is a permanent component or temporary? Yes, it is a temporary component which will die out as the time goes on. Am I right? So, what is the formula for steady state current? Steady state current means just very simple. Current is equal to voltage by impedance. That's all. So this voltage Vm by impedance, that is square root of R square plus X square into sin omega t minus alpha, where alpha is nothing but a power factor angle. Understand or not? This is steady state component. Similarly, what is the formula for a transient component? Yes, transient component will be, yes, Vm by root over R square plus X square into e power minus t by tau. Am I right or not? So indirectly, let me remove this. transient component will be some constant k into e power minus t by tau. I am not going into the proof of these equations. You will study in network theory more in detail. So this is a steady state component and this is a transient component, and if you look at the transient component, it is a sinusoidal component or non-sinusoidal component? Definitely non-sinusoidal. If you carefully observe, it is an exponentially decaying component, e power minus t by tau. What is mean by tau here? Tau is nothing but time constant of this RL circuit. Understand or not? So therefore, transient component is not a sinusoidal component, it is exponentially decaying component. That means, can I say it is a DC component? You can find out this constant k by implementing first order equation. Okay, write the differential equation and find the roots. You will find out the value of k. I am not bothering about it. Okay, presently I am talking about the nature of this transient component. This transient component is sinusoidal or non-sinusoidal? Non-sinusoidal, exponentially decaying. That means I can say it is a DC component. Am I right or not? Whereas steady state component is sinusoidal or non-sinusoidal? Yes, steady state component is purely sinusoidal, whereas supply source is sinusoidal. Understand or not? And it is available temporarily or permanently? Permanently it will be available, whereas transient component will be temporarily available. How much duration of time transient component will be available? You might have studied many times. In an RL circuit, transient current component will be available for 5 time constants. Am I right? After 5 time constants, the magnitude of this transient component will be almost equal to 0. Then only steady state component will be available. Understand or not? Concentration will be on time constant tau here. Tell me, what is the formula for time constant of a series RL circuit? We know time constant T is equal to L by R. For RC circuit, 1 by RC, like that. Now, suppose if this time constant value is equal to, let us say, 1 millisecond, then tell me, transient component will be available for how much duration? 5 time constants. That means 5 milliseconds, the transient component will be available. Suppose if this time constant is equal to 10 milliseconds, then transient component will be available for 50 million seconds. Okay, 50 milliseconds. So therefore, the time period for which the transient component is available will depend upon the time constant of this RL circuit. Now let me talk about an ideal transformer discussion here. I am talking about an ideal transformer. Can I say ideal transformer means losses can be neglected? If losses are neglected, indirectly the resistance offered by transformer winding is equal to 0. If resistance is equal to 0, look at this time constant. The time constant will become L by 0. That means indirectly time constant is infinite. Time constant is infinite seconds. That means you tell me, just substitute that time constant infinite here. If you substitute tau is equal to infinite, e power minus t by infinite, that is e power minus 0. E power minus 0 is equal to 1. That means the transient component will become a constant k. That means indirectly you tell me now, transient component will be a exponentially decaying component or pure DC component? Yes, this is going to be a pure DC component. There is no exponential term you see in this last equation. Am I right? And you tell me time constant is equal to infinite means the transient component will be available only for 5 time constants, or it is available for infinite time? Yes, transient component will be available for infinite period. Indirectly, transient component will be available throughout the operation of the circuit. Am I right or not? Okay, this is the discussion only if it is ideal transformer. So therefore, in ideal transformer, transient current component will be purely DC component and it will be available throughout the circuit operation along with steady state. But if it is a practical transformer, can I say resistance is definitely a finite value, because winding will have resistance. If resistance is a finite value, time constant is also finite value. If time constant is a finite value, this transient current component will be a pure DC component or exponentially decaying component. It will be exponentially decaying component and will be available only for 5 time constants. Am I right? After 5 time constants, the transient current component will die out, then only steady state component will be permanently available. So therefore, it is very important whether we are talking about ideal transformer discussion or practical transformer discussion. If it is ideal transformer, transient current component will be purely DC component and it will be available for infinite time. That means it is also steady state, right or not? If it is a practical transformer, resistance is a finite value, therefore time constant is also finite value. So transient component will be available only for a short duration, that is 5 time constants, after which transient component will die out. And what is the shape of the transient component in a practical transformer? It is an exponentially decaying current component, isn't it? So now indirectly, when you try to switch on a transformer from a sinusoidal voltage source, how many current components will be drawn by transformer circuit? 2 current components. One is a steady state, another one is transient. Most important thing, this is which inductance? This is leakage inductance or self inductance? This is the magnetizing self inductance of the transformer. As it is the magnetizing self inductance, can I say the current is nothing but magnetizing current only? Okay. And that means indirectly these 2 current components are nothing but current components in magnetizing current. So therefore, when you try to switch on a transformer, 2 magnetizing current components will be drawn. One is a steady state magnetizing current component, another one is transient magnetizing current component. Transient magnetizing current component is a DC component which is exponentially decaying and will be available for a short period called as 5 time constants, transient period. Steady state component will be a sinusoidal component and it will be permanently available. Understand or not? So now what happens here, as the 2 current components are available, definitely 2 flux components will also be produced. This steady state current component will create steady state flux component. This transient current component will create transient flux component. Am I right? So the total flux in the transformer is now sum of steady state flux as well as transient flux. Understand or not? So this is the minimum basics required to understand switching transients in transformer. Keeping this discussion in mind, we will move into our next concept. Okay, let's see. Now look at this transformer circuit. I have considered a single phase transformer which is under no load condition. As a transformer is under no load condition, what is the only current drawn by transformer? No load current. If I neglect core losses, then we are especially studying about magnetizing current. Core loss current is neglected. Now this magnetizing current, at the time of switching on, it has 2 components. One is a steady state component, another one is a transient component. Now my question here is that transformer is a highly inductive circuit. So therefore, look at this. Suppose the switch is assumed to be closed at a time instant t is equal to 0. That means you tell me what is the observation at t is equal to 0 minus. T is equal to 0 minus means before closing the switch or after closing the switch? Before closing the switch. Before closing the switch means it is open circuit. Therefore, what is magnetizing current value will be equal to 0. If magnetizing current is equal to 0, then what is the total flux inside the transformer core is also equal to 0. Suppose if it is a practical ferromagnetic core, the flux will not be equal to 0. Some small residual flux will be available, but I am neglecting that residual flux right now. Therefore, when a magnetizing current is 0, the total flux in the transformer core is also equal to 0. Okay. Now tell me, at t is equal to 0 plus, t is equal to 0 plus means immediately after closing the switch. Am I right? Once the switch is closed, what is our expectation? Current started to circulate here. But as I told you, transformer is a highly inductive circuit. Therefore, current does not change instantly. It will take some time for the current to change. Therefore, even though switch is closed, can I say magnetizing current does not change instantly? Magnetizing current does not change instantly means the value of magnetizing current will be same as T is equal to 0 minus. In T is equal to 0 minus, what is magnetizing current? 0. Therefore, the new magnetizing current is also equal to 0. Why magnetizing current does not change suddenly? Because transformer is a highly inductive circuit. It does not allow sudden change in current. If a magnetizing current is still 0, can I say the total flux in the transformer is also equal to 0? This is permanently or at the time of switching? At the time of switching. Am I right? But we know one thing. The total magnetizing current has how many components in it? Two components. One is transient component, another one is steady state component. When you add both of them, the resultant current should be equal to 0 at the time of switching. Therefore, the total flux in the transformer core must also be equal to 0 at the time of switching. But you tell me this total flux will have how many components in it? Again, as a current has two components in it, steady state and transient. Similarly, flux will also have two components in it. One is steady state, another one is transient. Whereas steady state flux will be purely sinusoidal and transient flux will be sinusoidal or exponentially decaying. However, if you assume it is ideal transformer, can I say that the transient component will be purely DC component? That is what we discussed. Actually, it must be e power minus t by tau. If you assume ideal transformer, that tau is equal to infinite. Therefore, transient component will become a purely DC component. In practical transformer, it is exponentially decaying. I will consider ideal transformer discussion first. Later, we can consider practical transformer discussion. So, total flux is equal to combination of steady state flux plus transient flux. Am I right or not? Now, to understand the shape of the steady state flux, we have discussed already. Steady state flux will be purely sinusoidal and it is permanently available from no load to full load or any condition. Whereas transient flux is not sinusoidal, it is exponentially decaying and will be available for 5 time constants. Suppose if it is an ideal transformer, this transient component will be purely DC component and available permanently again. Am I right or not? Okay. Now, let me try to discuss two important cases here. The first one is, let us assume, please listen very carefully, this is theoretical concept, very important. We will be discussing about two switching in transient conditions. First one is, at the time of switching, assume supply voltage is crossing its zero value, because you tell me one thing, transformer is switched on from AC voltage or DC voltage? AC voltage. As it is a time varying voltage source, you don't know what is the value of supply voltage at the time of switching. Therefore, I am considering two cases here. First case is, assume that transformer is switched on at an instant where supply voltage is crossing its zero value. Second case is, assume transformer is switched on at an instant where supply voltage is crossing its maximum value. Two cases I will consider. The first case is, assume that transformer is switched on at an instant where supply voltage is crossing its zero value. Supply voltage is crossing its zero value. Okay, let me draw the phasor here. I am taking voltage on y-axis, supply voltage, and I am taking time on x-axis. Okay, as I told you that we are discussing about a condition where transformer is switched on at an instant where supply voltage is crossing its zero. Assume this is the time t is equal to 0. At this instant, supply voltage is crossing its zero value. Yes. Assume this is supply voltage waveform. You see, at the time instant t is equal to 0, this supply voltage phasor is crossing which value? Zero value. The second case I will discuss, transformer switched on at an instant where supply voltage is crossing its maximum value. That is the second discussion. Okay, this is the first discussion. Now let us also try to draw phasor diagram of the transformer here. If you consider main field flux as reference, this main field flux means can I say mutual flux of the transformer, and induced EMF is always lagging the flux by 90 degrees, and supply voltage will be always opposite to that induced EMF E1. Am I right? This is the phasor diagram we know. And we also know that transformer is a constant flux device. From no load to full load, the RMS value of the flux remains constant in transformer. That is nothing but main field flux. Therefore, whether it is no load condition or full load condition or half load condition or starting condition, ending condition, whatever may be the condition, this main field flux does not change. That's why this is the steady state flux component in transformer. This is a steady state flux because it is permanently constant. Okay. Now you tell me, if you assume supply voltage is at an angle 0, reference, it is the reference, then this steady state flux component is lagging supply voltage or leading supply voltage. We know clockwise direction means it is lagging supply voltage by exactly 90 degrees. That means main field flux is at an angle minus 90 degrees. Okay. So therefore I can repeat, if a supply voltage was taken as reference, main field flux is lagging the voltage by exactly 90 degrees. Can I represent the same thing in this diagram? This is a supply voltage. Now main field flux will lag the voltage by 90 degrees. Lagging means, can I say, after supply voltage exactly at 90 degrees. This is 180 degrees. Here we have 90. So therefore, this is going to be the steady state flux waveform. It is lagging supply voltage by how many degrees? 90 degrees. So this blue color waveform is nothing but steady state flux in transformer, that is purely sinusoidal. We discussed already. Okay. Now we know supply voltage waveform and we know steady state flux waveform also. Let us try to find out transient flux component here. Okay. Please remember this phasor diagram. This is our reference. If you take main field, if you take supply voltage as reference, steady state flux or main field flux is lagging the voltage by 90 degrees. That is what I have shown here. Okay. Now see, we know total flux in transformer is equal to steady state flux plus transient flux. As a transformer is highly inductive, at the time the transformer is switched on, what is the total flux in transformer? Let me show you. Yes, look at this. At the time of switching on, can I say, as magnetizing current is 0 because transformer is highly inductive, it does not allow sudden change in current. Magnetizing current is 0. That's why even though the switch is closed, the total flux should be equal to 0 at any cost. I am neglecting residual flux, don't forget that. Total flux should be equal to 0. But this total flux is only steady state or only transient or sum of the two? Sum of the two. So therefore, coming to this point, now what should be the total flux at the time of switch closing? The total flux should be equal to 0. Am I right? And what is the steady state flux or main field flux value at the time of switching? So main field flux value will be equal to, at the time of switching, t is equal to 0. From this waveform, can I say this steady state flux value is equal to this much? Can I say this is nothing but minus maximum value of flux? Am I right or not? So steady state flux value is minus phi maximum plus transient flux. Okay, this is at the time of switching. From this, can you separate transient flux magnitude? Therefore, transient flux magnitude is equal to plus phi max. And I already told you that if it is a practical transformer, transient component will be exponentially decaying. But if it is a ideal transformer, this transient flux will be a pure DC component. Okay, pure DC component. And what is the magnitude of transient flux is equal to plus phi max, and it is a pure DC component if it is ideal transformer. Let me draw transient flux component also. Steady state flux component is minus phi max, transient flux component will be plus 5 max, and it is a DC component, most important thing. And it is permanently available if I consider ideal transformer. Okay, this is plus 5 max. Understand or not? So therefore, how many flux components are available right now in the transformer core? Two flux components. One is steady state, another one is transient. Steady state flux is purely sinusoidal and transient flux is purely DC component. Therefore, resultant flux is equal to 0 at the time of switching. Am I right? So let us try to draw waveform of the total flux or resultant flux here. Can I say resultant flux is sum of steady state flux and transient flux? Yes. At the time t is equal to 0, what is steady state flux value? Minus 5 max. What is the transient flux value? Plus 5 max. If you add both of them, the resultant flux is equal to 0. Can I say that is satisfied in inductive circuit? Yes or not? In inductive circuit, why total flux is 0 even though switch is closed? What is the answer? That is the point I am repeating every time. Even though switch is closed, why flux is equal to 0? Total flux is equal to 0. Because transformer is a highly inductive circuit. Even though you close the switch, magnetizing current remains 0 for a short period of time. As magnetizing current is 0, total flux in the transformer core also 0. Why magnetizing current remains 0? Because transformer is highly inductive, it does not allow sudden change in current. Okay? So that's why the total flux is equal to 0. If it is a practical transformer, total flux is equal to 0 or it will be equal to residual value. Yes, it will be equal to residual value, but that I am not considering, neglecting. Okay? This is the total flux at the time of switching. Very fine. But my question is, after one half cycle, what is the situation? Not at the switching, after one half cycle. Can I say after one half cycle here, at this point you tell me, what is the value of steady state flux? Look at this steady state flux. Can I say steady state flux value is equal to plus 5 max? What is the value of transient flux also? Plus 5 max. Steady state plus 5 max. Transient also plus 5 max, then what is the resultant flux will be equal to 2 times of 5 max. Okay, the resultant flux will be somewhere here, which is equal to 2 times of 5 max. That is immediately after the switching or after one half cycle? After one half cycle. Look at the next half cycle. In the next half cycle, can I say steady state flux is minus 5 max? Transient flux is plus 5 max, therefore resultant flux is equal to 0. That process will continue. Therefore, if I draw a waveform, this is 0 total flux, 2 times of maximum, 0. Yes. This is how the waveform will continue. Alright. So therefore our observation here is that this red color one is nothing but total flux or resultant flux in transformer core. And what is the peak value of the resultant flux right now? It is 2 times of actual maximum value. That is what we will call it as doubling effect in transformer circuit. Okay, we will call it as doubling effect. Flux is doubled. Rather than a rated maximum value, the resultant flux reaches to 2 times of maximum value. We will call it as flux doubling effect. Now, will you tell me one thing? This is all the discussion we are considering when you try to switch on the transformer at a time instant where supply voltage is crossing its 0 value or maximum value. Yes, supply voltage is crossing 0 value. That's why steady state flux is minus maximum. If steady state flux is minus maximum, transient flux is plus maximum, therefore after one half cycle both are adding and resultant flux becomes 2 times of actual maximum value. Am I right or not? So that means you tried to design the transformer for 1 time of maximum value, but unfortunately the flux reaches to 2 times of maximum value, which is called as doubling effect of transformer. Okay. Now, what are the disadvantages? What are the consequences of this doubling effect? We need to discuss now. Okay. Now, let's see what are the disadvantages of doubling effect. So, what is the doubling effect? First of all, this is the phenomena experienced by a transformer when we try to switch on the transformer at an instant where supply voltage is crossing its zero value. If supply voltage is zero, resultant flux will reach 2 times of the actual maximum value. Therefore, core will be saturated simply. We know practical transformer core will have a magnetic saturation effect. Now see, I am considering a magnetizing current here and flux, resultant flux on y-axis. We know every ferromagnetic material will have magnetic saturation effect like this. Am I right? So generally transformer is designed to operate along which point in magnetization curve? It will be designed to operate along knee point. Knee point means somewhere here. Therefore, corresponding to this point, it is the rated magnetizing current. Corresponding to this point, this is the actual maximum flux of the transformer. Okay, this is the rated flux indirectly. But due to this doubling effect, transformer flux reaches to 1 time of maximum or 2 times of maximum. 2 times of maximum. That means, can I say this flux is just doubled? 2 times of flux maximum means somewhere here. Flux is doubled means, you see now the point existed in linear zone of magnetization curve or saturation zone. Yes, it will went into deep saturation zone. What is the disadvantage of transformer saturation or core saturation? The disadvantage is, we know in this saturation zone, a small rise in flux demands a large rise in magnetizing current. Am I right? Suppose if it is a purely linear curve, what happens? If it is like a straight line, if a flux is doubled, magnetizing current also just doubled. That's all. That is not a big problem. But practical core will have a linear magnetization curve or non-linear. This non-linear magnetization curve will saturate transformer core, and in this saturation zone, a small rise in flux density itself will demand a large rise in magnetizing current. Therefore, a doubling in flux will make magnetizing current dangerously high. Okay, dangerously high. So usually these large magnetizing current due to doubling effect will be 15 to 20 times of rated current. If rated current is, let us say 100 amperes, that large magnetizing currents may be 1500 to 2000 amperes also. Okay. So why such a large magnetizing current is demanded? Because of magnetic saturation. It is a small saturation or deep saturation, very deep saturation. Even a small saturation also sufficient to draw large current. Okay, therefore a deep saturation will draw dangerously high magnetizing currents, and those dangerously high magnetizing currents are called as magnetic inrush currents. We will call them as magnetic inrush currents. Okay, so what is the range of magnetic inrush currents? Magnetic inrush currents will be usually 15 to 20 times of rated current. Why large magnetic inrush currents are drawn? Because of core saturation. Why core is saturated? Due to doubling effect. Why doubling effect came into picture? Because of transient flux component. And this is the entire discussion when you try to switch on a transformer at an instant where supply voltage is crossing its zero value. Okay. So if you try to switch on a transformer where supply voltage is crossing zero value, definitely this doubling effect will come into picture and large magnetizing currents are drawn. They are called as magnetic inrush currents. Okay. So the magnitude of magnetic inrush currents will be 15 to 20 times of rated value. And most importantly, you tell me, if it is ideal transformer, this transient flux component will be available for a short period or very long period? Yes, it will be for a very long period. Therefore, magnetic inrush currents will also be drawn for a long period. Winding will overheat due to excessive copper loss. Transformer will damage. But in practical transformer, you tell me this transient flux component will be a purely DC component or exponentially decaying? Exponentially decaying. Therefore, that doubling effect will also be exponentially decaying. Therefore, these inrush currents will be available for a long period of time or short period of time? Short period of time, at least for 5 time constants. After 5 time constants, transient flux component will die out, then resultant flux will reach 2 times of maximum or 1 time of maximum. 1 time of maximum, in that case, inrush currents can be avoided. Am I right or not? So therefore, in practical transformers, inrush currents will be available for how much duration? Means what is answer? 5 time constants. If each time constant is 1 millisecond, then inrush currents will be available for 5 milliseconds only, very short period. As the inrush currents are available for a very short period, those inrush currents will damage a transformer or cannot damage? Cannot damage. Why? Because even though inrush current is very large in magnitude, it will take some time for the copper loss to rise the temperature. Am I right? Within a short period, temperature will not rise suddenly. Am I right? Therefore, inrush currents are not so dangerous because they are available only for a short period. Okay? But inrush currents are very dangerous in case if they exist for long period, because they will create 2 disadvantages. One is excessive copper losses because of very high current magnitude. Second one is unnecessary mechanical forces on transformer winding, because when current becomes dangerously high, leakage flux value will also increase. Therefore, mechanical forces experienced by transformer windings will also increase. That will also reduce the life of the transformer. Okay. So therefore, make sure that during the design stage itself, try to make sure that inrush currents are available only for a short period of time. Okay. So this is about magnetic inrush current components. Okay. So the summary here is that when you try to switch on a transformer at the time instant where supply voltage is crossing its zero value, when voltage is zero, steady state flux will be minus maximum, because flux is lagging the voltage by 90 degrees. When steady state flux is minus maximum, transient flux will be plus maximum. Then only the resultant flux is equal to 0, inductor property is satisfied. But after 1/2 cycle, steady state flux reaches to plus maximum, transient flux also reaches to plus maximum, resultant flux becomes 2 times of maximum. That will saturate the transformer core deeply, therefore dangerously high magnetizing currents will be drawn. They are called as magnetic inrush currents. Okay. Now, our next discussion is what happens if transformer is switched on at an instant where supply voltage is crossing its maximum value. Okay. If a supply voltage is crossing its maximum value, then is this doubling effect will be present or not is our discussion. Okay. Let's see. Now see case number 2. When a transformer tried to switch on at an instant where supply voltage is crossing its maximum value. Now look at this waveform. This is the time t is equal to 0. At a time t is equal to 0, supply voltage is crossing its maximum value or 0 value? Maximum value. And we know from the phasor diagram of transformer, steady state flux will lag the supply voltage by how many degrees? 90 degrees. That means if a supply voltage waveform is like this, can I say steady state flux will be lagging this voltage by exactly 90 degrees? So this blue color waveform is representing steady state flux value, and can I say steady state flux is lagging supply voltage by exactly 90 degrees? Yes. Therefore, you tell me now at the time t is equal to 0, what is the value of a steady state flux? Can I say steady state flux value will be equal to 0? At the time t is equal to 0, that means at the time of switching, steady state flux is 0. And at the time of switching, what should be the total flux in the transformer also? That must also be 0. Why? Because transformer is highly inductive. It does not allow sudden change in current. So the total flux at any cost at the time of switching should be equal to 0. Already from the from the waveforms, steady state flux is 0. Now, will you find out what is transient flux in the transformer core? Therefore, transient flux will be equal to 0. From this, can I say transient component flux is not at all produced? First of all, it is equal to 0. If transient flux is equal to 0, then what is the only flux that will be permanently available? Steady state flux only. Steady state flux only means the maximum value will be 1 time of maximum or 2 times of maximum. 1 time of maximum only. That means doubling effect is avoided. If doubling effect is completely avoided, can I say magnetic saturation is avoided? If magnetic saturation is avoided, can I say large inrush currents will not be drawn? So therefore, if you wanted to avoid magnetic inrush currents, it is better to switch on the transformer where supply voltage is 0 or supply voltage is maximum. Supply voltage is maximum. But you cannot give guarantee about it because supply voltage is continuously changing. It is a time varying value. So we have to design the transformer to withstand magnetic inrush currents always. When magnetic inrush currents are producing, when you try to switch on a transformer at an instant where supply voltage is crossing its 0 value, okay? And you tell me magnetic inrush current is only steady state current or only transient or sum of the two? Yes, sum of the two. If it is a practical transformer, that transient current component will be exponentially decaying and it will die out after 5 time constants. Therefore, let me try to draw the shape of magnetizing current if transient current component is available. When inrush currents are going to be produced, when we try to switch on the transformer at an instant where voltage is crossing its 0 value. Okay, so see the shape of the magnetizing inrush current I am trying to draw. It is a sum of steady state current as well as transient current, where steady state current is sinusoidal and transient current is exponentially decaying if it is a practical transformer. Therefore, the total shape of the current will be like this. Yes, this is how the shape of the magnetizing current will be. If you look at that, it is exponentially decaying. Once a transient component completely dies out, then what is the only current that will be available? Steady state current only. Understand or not? Now, will you tell me, during the initial transient period, the shape of the current will be definitely purely sinusoidal or non-sinusoidal? It is non-sinusoidal, that too unsymmetrical. As it is unsymmetrical, it will be definitely rich in second harmonic. Okay, magnetizing inrush currents are rich in second harmonic because during the transient period, it is a combination of sinusoidal current and exponentially decaying current. The sum of the two will be a non-sinusoidal unsymmetrical waveform. Therefore, magnetizing inrush currents are rich in second harmonic component. They are rich in second harmonic. Okay. Now the question here is that what is the magnitude of magnetizing inrush current? Yes, the magnitude of magnetizing inrush current is 15 to 20 times of rated value. 15 to 20 times of rated value means, can I say definitely very high magnitude? As it is very high magnitude, can I say it is like a fault current in power system? Because whenever some short circuit fault takes place, definitely current becomes very high in magnitude. Okay, and magnetizing inrush current is also very high in magnitude. But the difference between the two is, if it is a magnetizing inrush current, it will automatically die out after 5 time constants. But if it is a short circuit fault current, it will be continuously available till you clear that fault. So therefore, whatever the protection equipments that we are using, like relay circuit and circuit breaker, they must be in a position to sense whether the coming large current is inrush current or fault current. Why? Because inrush current means it is a natural phenomena and it will die out automatically after 5 time constants. Whereas short circuit current is a forced phenomena and it will continue to flow till you clear the fault. Therefore, the relay circuit should try to protect the transformer against inrush current or against fault current, against fault current only. It need not to protect a transformer against inrush current because inrush currents are only for short duration. Okay. So therefore, every relay circuit we are using for a transformer, they should be in a position to separate inrush currents and fault current. That means they should be in a position to sense whether the large current coming is inrush current or fault current. That is just by sensing this second harmonic component. A large current is sensed by a relay, and that current has a second harmonic component. That means definitely that is which current? Inrush current. A large current is coming. okay, more than rated current, but that is not having second harmonic. That means that is which current? Fault current. So relay should operate only for fault current or also for inrush current? Only for fault current. That means current is more than rated value and it is not having any second harmonic. Definitely that is a fault current. Relay should operate immediately. A large current is coming more than rated current, but that is having a second harmonic. That means indirectly it is magnetic inrush current, so relay should not operate. That's why every relay circuit used for transformer protection will have an important coil known as second harmonic restraining coil. Second harmonic restraining coil. Okay, so presence of this coil will sense whether that current is having a second harmonic or not. Imagine I have a transformer circuit whose rated current is, let us say, 100 ampere. Okay, that means if current is equal to or less than 100, definitely transformer will not damage. But suddenly a 1000 ampere current is coming into picture. Definitely 1000 ampere has the capacity to damage a transformer. But this 1000 amperes is a short circuit current or inrush current. How the relay will sense? By sensing second harmonic component. If this 1000 amperes has a second harmonic component in it, definitely that is inrush current. So no need to operate relay because this will die out very soon. But if this 1000 amperes do not have any third harmonic component, that means definitely it is a short circuit current. Relay must operate. So it is very important to have a second harmonic restraining coil. You will study more in detail in power system protection, subject, why this second harmonic restraining coil is required, where do we place, how it operates, everything you will study in overcurrent relays in transformer protection. Okay. So this is about switching transients in transformer. So tell me, when inrush currents will be possible? When you try to switch on a transformer at an instant where voltage is crossing its zero value. When inrush currents can be absent, when you try to switch on a transformer when voltage is crossing its maximum value. But is it possible always to switch on the transformer at maximum voltage point? No, because our supply voltage is continuously changing with respect to time. Therefore, it is not possible. 100% accuracy cannot be met to switch on at an instant where voltage is crossing its maximum value. Therefore, every transformer must be designed to withstand inrush currents at least for a short period of time. Okay.